Good afternoon and welcome to this webinar provided by bobwillis.co.uk. We also welcome delegates from the SMTA. My name is Bob Willis and I'll be presenting today's webinar. Before we start talking about our subject today, pin-in-hole intrusive reflow, let's move on. So pin-in-hole intrusive reflow, it's been around for quite a few years and I wrote the first book on the subject. I also produced the very first video training on the subject, and you can visit and download this book free of charge from the website I've indicated here, and it's run by 007 magazine. Again, it goes into nearly all of the detail that I talk about in the presentation, and hopefully it will be a reference source for you in the future. So first of all, advantages to the process. What it does is eliminate potentially manual and wave soldering with a process you're all familiar with. If you're reflowing product 9 times out of 10, you can use this technology, and it only requires small changes to allow you to do it effectively. It's compatible with your printer, it's compatible with your reflow process, and it may well be compatible, that is the connectors, with your SMT assembly process, if you can make sure that you have pickup tools to accommodate them. Minimum implementation cost, all it needs is another stencil, possibly a change in the connectors to stand up to higher temperatures, but literally the implementation cost is very, very small. Increased automation, potentially, because quite often we assemble a connector or 2 connectors on a PCB, and those are done as a manual operation. So if we can automate it, then certainly we can automate the soldering process, so consequently, potentially, it's an advantage to us. It reduces floor space, and if you think about it, the wave soldering process, the selective soldering process, does take up quite a lot of room, and it does take up a lot of energy. So if you could reduce the number of products that are going through selective, wave, or hand soldering, then again that gives you more space in manufacture. It also works with LTS, low temperature solder, and with low temperature solder it potentially allows you to use connectors which have a lower specification in terms of peak temperature. Other advantages: reduce capital equipment. So if you are setting up a brand new process and the process board design required originally selective or wave soldering, you could eliminate that capital expenditure, which again gives you the other advantages we've previously talked about. It's only one heating process potentially. Now, most companies will do double-sided reflow, so you're doing 2 reflow operations, but you're also soldering your through-hole parts as well. Now, potentially, you could do the whole process with 1 heating process. Now, this is kind of unusual, but it's something I have done in the past where we've done double-sided reflow and pin-in-paste simultaneously. So if you look at the book that I was mentioning, the free download on pin-in-hole assembly, it will talk about simultaneous double-sided reflow soldering, and that might be an option to you. Overcomes multi-layer issues. One of the nice things about reflow is it brings all the board up to temperature. So consequently, slowly bringing the board up to temperature rather than using preheat on wave and preheat on selective, which can still give you variation on thermal demand, you're getting the core board up to temperature. So again, better solder penetration on very heavy multi-layer boards. That is a potential advantage. Reduced health and safety, and the reason I mention this is because when you look at the higher soldering temperatures we use for lead-free technology, the materials we use, if we can eliminate those from the assembly process, then there's less things to consider that might be harmful in manufacture. We're only talking about the requirements for the reflow process. So potentially there's an advantage there. So let's just step through the basic process so we know what we're talking about. Well, with any reflow process, we're printing solder paste. Now, incidentally, I will talk about jetting solder paste and dispensing solder paste for intrusive reflow as well, and give you some results from an old study of mine. But predominantly, most people will be printing solder paste through a stencil to achieve both reflow and intrusive reflow in one operation. So basically, we're using a stencil, something you're very, very familiar with. Printing paste across the surface of the stencil, through the apertures on the printed circuit board, and depositing solder where we require it on pads. This is a standard open printer, which the majority of the industry use for printing technology. However, you can use a sealed head printer as well. This is an example of an old MPM sealed head Rio pump, where the solder paste is retained within the pump head. And the advantage of this is for thicker boards, we can actually push the paste further into the plated through hole. The same is also true for the specialist head on deck printers. Here you see an example of a sealed head unit. And again, the solder paste is held within a cartridge in the head. So printing as we would normally do, but potentially we've got the advantage of applying pressure to the paste, which again increases the penetration into the through holes. However, the standard blade printing process does work. These other two techniques just give you another variable that you could look at to improve your process still further. So when we look at printing, we're printing through a stencil onto the surface of a board. And what I'm showing you in these two video clips is printing onto glass. So you can see in the first example, I'm printing onto multiple areas, and these are in fact on a 96-way connector. And on the bottom right, I've just shown a video where you can see the solder paste fill an aperture, which is kind of a strange shape, but we're actually printing onto a hold down feature on a connector, the thing that mechanically holds the connector in place on the board. So it's got a mechanical function as opposed to electronic function. Now we'll see examples of these connectors being processed a little bit later on, but they're just an example of how we modify and shape the stencil aperture to suit the requirement, but also to suit the necessity of the particular connector design you're using. So we print paste. We may have already assembled side 1 and we're moving on to side 2. We populate side 2 and then we insert the through hole. Now, again, if we're looking at manual assembly, you probably still do it the same way. So surface mount first, then manually populate the through hole component. But you could, if you wished, place the through hole component first and then populate around. It depends on the clearance areas from your machine, and also we've got to consider that when we're inserting a connector, we don't want to move other parts on the board. So you've got to look at which way you do it. Typically, most people today normally insert the connector as the last step, but again, it depends on your own operation. So when we reflow, what will happen is the solder paste will coalesce, as paste does during reflow, and be drawn into the plated through hole. So the key thing is getting the volume of paste right to get what you require in terms of a solder joint. So typically, what we're trying to do is get a minimum 75% fill of the plated through hole, and we should be able to do that quite successfully. If we get our hole to lead ratio right, if our connector allows us to print the required volume of paste, we can get a full 100% fill of the plated through hole. It's perfectly achievable, although the 75% will give mechanical strength and rigidity for most products, so it shouldn't really be an issue. And certainly my experience is I've never seen a plated through hole solder joint fail yet. Now, just to give you another perspective, here is an X-ray of reflow. And you can see both top and bottom solder fillets reflowing in this example. So the top side is where the bulk of the paste would be, and the bottom side is just what paste might be present on the tip of the pin. And if you watch reflow taking place as you see it now, you can see the paste reflowing and being drawn into the plated through hole. So what you end up with is a perfect joint. So let's look at how we're going to achieve this in our process. Now, this is just an old video I made for a good friend of mine who originally was with Indium Corporation, now with Alpha, and it was just showing what was actually happening in the reflow process, but in a sectional view. So I took a board, I sectioned half the board, half the pin, and assembled it just to show the paste reflowing, but also being pulled back into the plated through by capillary action. So it's just another way of looking at how a joint forms. However, the X-ray example is by far the best way of understanding the process of intrusive pin in paste, selective paste reflow, whatever you want to call it. In fact, in Japan, they used to call it multi-spot soldering, which we may mention a little bit later on. So there are lots of different design connectors in the marketplace. There are also some other through-hole parts which can be reflowed, and it comes down to their compatibility with the temperature of reflow. That's primarily the thing to look out for. So you can see in here we've got some different shaped parts. We've got 5-row pins, 3-row pins, 2 step pins, and we've also got these hold down features which I was mentioning. So on the left hand side photographs, the DIN connector and the 9-way connector both have hold down features as well as electrical and mechanical connections. So again, we change what we do and how we do it based on the pin and the pin design. So the key things about the components is material compatibility, first of all. Will it stand up to temperature? But if you're considering using low temperature solders, which reflow somewhere between 180 200 degrees Celsius, it's significantly lower than lead-free or SAC alloys. So consequently, you shouldn't really have a problem if you were using these. The component standoff height is the key thing. Can we print underneath the connector, or can we print first and then insert the connector and the connector not come into the contact with the solder paste? So standoff. So standoff typically on most connectors will be somewhere between 0.008 of an inch and 0.010 of an inch for a connector. It's normal because they allow for outgassing of volatiles during the wave soldering or selective process. There's normally always a gap around the pin to allow this to occur. Assembly handling. Now, can we automate it, or will it always be manual? And how do you get the parts supplied to you? Is it in a plastic bag? Is it in a box? Are they separated? Again, it's the quality and consistency of the connector pins, and no damage to the pins is a key thing. Component lead length, as a basic guide, the pin length protruding below the board should be between 1 to 1.5 millimeters. You don't really want it any longer than that, and I'll explain later. You could have it shorter. In fact, some designs for high frequency have connector pins which are the same thickness as the board. So you don't actually see the tip in the solder joint you're actually producing. So again, it depends obviously on the requirements. So here's some examples of not compatible components. I'm sure you can relate to this. And each one of these has been reflowed, but you can see they're severely damaged. So these components weren't compatible with the soldering process. You may have made great solder joints, but you won't have been able to connect these to anything else on the printed circuit board or on a mating connector. So again, minimum requirements. If we look at standoffs, please be aware that if you select a connector, let's say a connector from Harting or Amphenol or Harwin or whoever is making the connector. You're designing for that connector. Please make sure the purchasing department don't change the connector supplier to save a few pence. Now, if they need to, and you can show a good cost saving going to another supplier, that's fine, but you must re-look at the connector and the position of the pins in relationship to the standoffs. So what I'm showing you here is just the pip standoffs that may be on the connector, and they're there to stand the connector off the board to allow the plastic not to make contact with the PCB. It allows gas to escape during the soldering operation and reduces the possibility of defects associated with plugging the top of the hole. So with standoffs, they may be strips, they may be individual square pins. Just look at where they are on the alternative supplier. But you've obviously got to look at them to start off with to make sure they're not going to be affected, or you're not going to affect the printing operation because of them. So simple things like this, you've got to plan and plan for any change if necessary. So here's just an example of the bottom of two IDC connectors, so double row IDC connectors, and you can see made of two different plastics, but the standoff pips are in one example on the right hand side on the white plastic part, just on the outside extremity of the connector. However, if you look on the black connector, the standoffs are around the pins. So you have a restriction of where you can print solder paste on the surface of the printed circuit board. It may or may not have an impact, but know in advance what potentially can displace the paste during insertion of the connector. Now in this example, this is a multi-way connector, and you can see we've got staggered pins. You can also see that between the rows of pins, you've got part of the plastic molding, which is basically giving you the support, the standoff from the surface of the PCB. But because you've got this staggered approach, what we can do is print long strips of paste rather than squares or rounds, and they can sit within that area which won't come into contact with the connector. So we can adapt things, but again, it's engineering. The connector is the number one thing. I often find that stencil manufacturers are asking design engineers or process engineers for examples of the connector that you're going to be using. And I'm often told by the stencil manufacturers they find it very difficult to get samples. So please help your stencil manufacturer by providing a sample if he asks for it, because he's trying to help you get the best stencil design for your particular product. Kind of strange, but perhaps it's not explained correctly when it goes from supplier, purchasing, engineer, purchasing, supplier. So understand both sides. He's trying to help you. So on this type of connector, again, we've got multiple pins, 3 rows, but we've got a hold down feature. So basically that is holding the connector in the board. You can also buy exactly the same connector without any hold down feature at all, and just rely on the pins giving mechanical and electrical support, which I found works pretty well, particularly where you've got nearly 100 pins. But if you have got a hold down feature for a specific reason, we've got to accommodate that, because as you can see, the plastic on the connector is flush with the hold down feature. So if you're putting paste on the board and on the surface of the board, then you'll probably generate solder balls during reflow. So let's just understand how we overcome that as we go through this process. So if we look at the basic guidelines for any soldering process, and this is what I use for any soldering process, I don't really differentiate. So I take the pin size, so the maximum pin size across the corner, so the worst case biggest pin size. I add 10 thousandths of an inch to it, 10 thousandths of an inch, and that is my finished hole size I put on my specification, not drilled hole size, finished hole size. And that finished hole size is after plating, after copper, after nickel gold, after whatever coating. If it's solder leveled, there's more variability with solder leveled boards. So again, that's what you need to specify to your supplier. So it's the finished hole size we're talking about, not drilled, finished hole. That's what should be on your specification. So we've got the option sometimes of getting different pins on connector parts or components. So, be aware that a round pin is ideal because it takes up more area within the plated through hole, and then you don't have to put so much solder paste in or on the surface. Square is next, and oblong less of an opportunity. However, you'll probably find today that most pins are oblong because they're cheaper to manufacture. So that's what we're really looking at in most situations. The others make it slightly easier for us, the oblong slightly more difficult, but we're perfectly able to produce reliable solder joints with oblong pins as well. So this is basically my go-to design rule. Pin size, maximum pin size across the corners, the biggest part of the connector pin, plus 0.010 of an inch is your finished hole size. But if you look at most connector manufacturers, the holes they recommend are way too big. So don't work to the component manufacturer's recommendations if you're going to be running parts in this particular type of process. So just to show you some examples of how we've modified things on these designs, on the top we've got modified stencil apertures to give greater volume. So on the left-hand side, as opposed to the bottom left-hand side, we've got square holes. You'll get greater volume of paste with a square hole, and it still allows you to print successfully for this 100-pin connector. And again, with the hole where we've got the hold down feature, you can see that we've put these crosshairs in, and you'll see why we do this a little bit later on, but it's all to do with paste into the hole and not onto the surface of the board. So this allows us to solder to the hole but not actually squash paste when we assemble this type of connector. So each one of these connectors that you come up against might need slightly different design rules that you have to adopt for your stencils. So that's why I say it's useful to talk to your supplier. And on the right-hand side, we're going to show some slightly different design rules. And again, it's all about the connection. Can we get more paste, or can we overcome a particular facet of the design of the connector to allow us to assemble successfully? So taking an example, my 96-way connector. This is I normally use this because it's the connector I use on all my training boards for Intrusive Reflow. So my go-to stencil aperture size is 80 thou by 80 thou on a 6 thou stencil, and we've got 110 thousandths of an inch by 10 thousandths of an inch apertures opening. This allows me to print successfully into the plated through hole for a hold down feature. So if we look at a couple of other things which some people do, I personally don't do, and it's not because it's bad, it's just I just don't really need to do it. And this is making visually it easier when you're training people to do pin and hole assembly manually. And what you've got here is we're printing paste into the hole, but allowing it not to be present on the surface of the pad. So what it does here is shows you where to put the connector. You can see the hole, because when you print over it normally you don't see where the hole is. So you have to judge it based on your own experience. Now, a skilled operator will be doing this day in and day out. It's not a problem. The first time they do a new design, it may take a few minutes to get right, but after that, it's pretty straightforward. But if you insert the connector and then reflow it, you quite often see this effect. So if there's any quality engineers on the call this afternoon, this is not a defect. This is kind of by design, if you like, where you can still see the base material visible because it was there to aid the assembly process. As I said, I personally don't normally use this trick, but I mention it because it's part of the whole process of pin-in-hole intrusive reflow. So going back to my example for one connector, here you can see I've got two different board finishes. One is copper OSP on the right-hand side, and one maybe tin or silver finish on the opposite side. But you can see we've printed with this stencil, and you can see that the solder paste deposit is not actually on the surface, it's more into the hole, but you can still see the crosshairs. And the nice thing about the crosshairs, one of the other things, is that when the paste is actually printed and goes into the hole, it's like, as I normally refer to it, sort of 4 sausages of paste in the hole, and they're pushed down up against the side walls. So typically you don't lose much volume if it's pushed out, or it's pushed out during the reflow soldering part of the process. So there is something there to solder in place. The other thing is the connector pin, because its position allows it to solder successfully. So just an example, operator, manual assembly on a production line. And this was actually a sales engineer who turned up with a bunch of connectors to run a production line with me many years ago, and they stayed all day. Well, that was their job, to sell connectors. So, but seriously, they'd never assembled any connectors in their life. And then after that, they were an absolute expert on manual assembly of connectors. Now, if you're doing manual assembly, you might need some form of guidance plate if you've already placed all your SMT devices beforehand. So actually having a plate over the assembly line where you can actually plug components directly into their positions with some sort of alignment aid like this, that works quite well. And it also virtually eliminates other components being knocked over or misplaced, either by the hand, the component, the arm of the jacket or work coat, or even the static strap. So again, it's just a nice little trick that kind of works, and not ideal for everybody, but it's something that could be used. Now, just an example of how to get it wrong. This is again a post header, and there's not any problem with it apart from the hole is too small. And you can see that I cannot get that into the plated through hole. It would have certainly caused a few problems in manufacture. So got to get the hole to lead ratio right, but it's not complicated or difficult. Pin length, I've mentioned. If you've got a board, and we've got one here, and I insert the connector into the board, if the pins are too long, what tends to happen is the paste is pushed out. Now, you won't push out all the paste, but you are wasting paste. You don't want it on the pin, ideally. You want it in the hole. But the other complication is with if you've got too long of pins, you're taking the paste away from the joint, which is one thing. But if for some reason you're using a different finish on the pins, and the paste reflows on the pins, you'll get this effect. And the quality department will be concerned you've got a de-wetting problem or a non-wetting problem on the pins. And it's all to do with the small amounts of paste being present on the pins. So again, 1 millimeter to 1.5 millimeters is perfect. If you need for electrical requirements less than that, i.e. flush with the board or even recessed into the board, as some companies do, again, that can work because mechanically it's extremely strong. Just an example of automated assembly. This is a machine on a production line I was running at Productronica. And what you're looking at here is a range of different connectors they are optically checked, they're picked and inserted into the board. Now, most surface mount placement machines can handle odd form components today. It's all about the tooling, and it's all about the packaging that you need to make this successful. So again, that's perfectly feasible to do, but again, you've got to look at the engineering you've got to put in to allow you to do that effectively. And again, this is a couple of other examples. I was working for a connector manufacturer introducing or helping introduce the use of pin and paste reflow. And we evaluated different placement machines' capability to handle connectors. And, you know, this was a few years back. I would suggest that nearly every pick and place company should be able to handle some level of odd form today with optical alignment and correction as well. Again, speak to your supplier, or if you're only putting one connector on a board, it's probably not worth doing it. It's easier to manually insert. Now, in terms of optical and optical alignment, obviously the longer the connector, the bigger the possibility of a problem, and also having the right packaging to protect the pins so they're not bent, because obviously if the pins are bent, then the machine doesn't understand and it will try and insert it. An operator is more flexible. So again, look at the vision capability of the system to pre-check parts prior to automatic assembly, which shouldn't really be an issue. Now you'll notice here we've got a hole. Now that hole is there for a particular reason in the design, and we actually used to use that for rotation error. So you could actually use the hole. You never printed into it. It was just a hole there for optical alignment, and on some machines that worked very, very well. And it overcame the variation in rotational error that could happen with large connectors. So again, that's just a little trick that can be used in manufacture. Now, a couple of other examples of pin and paste, just to show you there are some other techniques. And this is one technique where the board is assembled, but we're actually using dispensing to apply solder paste. So you're all familiar with dispensing systems to apply paste to a board for high-speed operation. You can use those systems, and we'll talk about that a little bit later on, but these are just a couple of traditional dispensing systems. And on the right-hand side, I just show an old high-speed video of pin and paste intrusive reflow, but actually using a specialist tool that goes over the top of the pin, which was developed specifically for that particular type of process. So there's lots of ways of using pin and paste intrusive reflow. It's not the most common, but it's, again, other techniques that can be used. Now, in this example, we're actually using a multi-nozzle system and applying paste to the surface of a board. That's another one. That was a proprietary system that a company actually designed and developed themselves for the process. So you'd use screen printing, but actually use a dispensing system, multi-nozzle, so you could get control of the volume of paste you were putting down in those days for this particular product. Finally, as an alternative technique, Sony, for those of you who still remember the days of Sony Discmans, the Sony Discman was made by intrusive reflow soldering for connectors and also for some passive components. And this is how it worked. You've got the board, you've got, again, a specialist stencil plate with pillars in where you'd force the solder paste down onto the surface of the board, as you see here. And then the board would then go through reflow, but it would be selective reflow. So here you can see hot nozzles or hot air being blown at the individual joints for through hole. And that was used for many, many, many years, I believe originally in Japan and then in India. And a friend of mine was kind enough to send me these photographs way back when this process was first introduced. So again, a lot of engineering tooling, but again, it's a process that, you know, might be adaptable for products in the future. Finally, in terms of variations or alternatives, some of you will be familiar with jetting technology. So this is an example of jetting of solder paste to the printed circuit board, which can be used for all your surface mounts, fine pitch, as well as through hole. And I did a little exercise a couple of years back using jetting technology. And I've always been a lover of the use of the jetting process because it's so flexible in terms of design changes. Advantages and disadvantages to any process, but certainly it's something I've always been very keen on. So this is just an example of jetting on my own test board, which you've already seen. It is a slow process because you've got 100 connectors and you're putting on multiple deposits for this particular connector. So this is not the best example of using, in this particular case, the My 500 or 600 or 700 now today, but it is capable of doing this type of process as an alternative to traditional printing. And on the My Data software, you can see here, you just pull in the design, and the beauty of this is it's quite quick to do. You just take your design data, pull it in. You can see the two connectors I've highlighted in yellow on this screen. I can then define how thick the board is, what the size of the connector pins are, what size the hole is, and there's a little algorithm in the software, or in the original software on the 500 when I did this work, that calculates how much is required in terms of dispensing or jetting technology to fill the plated through hole. And this is just an example of the dot pattern, if you like, for this particular type of connector. Now these are photographs taken or x-rays taken after jetting, before insertion of the connectors. I always like to do this because it's just a nice way of seeing hole fill with paste and what variability we might get. So this we did this as part of the exercise. Then we reflowed the boards. We did it with convection, and we also did it with vapor phase. And these are typical examples of the joints we produced. Again, all of them exceeding IPC 610, solder joint, 100% fill both sides on both of the processes that we were doing the work on. And these are just some x-rays. Again, we've got some positive fillets and some without positive fillets on the top side, if you look at the x-ray on the top right. But again, all of these exceeding IPC 610 without any real problems whatsoever. And just a couple of odd microsections that I made at the time. There's a few scratches in these sections, so I must improve my skills. But you can see 100% fill, perfectly good solder joints were actually the outcome of this exercise. I just wanted to include this bit about jetting because with the interest growing in jetting technology, it will never take over from screen printing in terms of mass production, but certainly it gives you that flexibility to do other things and also change very, very quickly the volume of paste you're actually applying. Another little exercise just on the same board, again, just to give you some practical experience of things that I've done on this board. I did an exercise with higher temperature alloy, lead-free alloy. This is the SN100C. This is the tin copper as opposed to the SAC material that we're all familiar with. Again, I used exactly the same design concept, design rules for printing and assemble this particular board with this material. And we ran it in convection and again vapor phase, reflow, but I had to go to ACW at the time because they were the only company with the right boiling temperature of fluid in the vapor phase. Other companies just didn't have the higher end. The material requires a slightly higher temperature to reflow because it's tin copper as opposed to SAC alloy, but still the peak temperature would be below most companies' peak reflow temperature in air or in nitrogen. So nothing really different. It's just a different way of processing. The other beauty of a lot of vapor phase is you can use vacuum if you want. So if you did actually have any void problems, you could overcome that. But that's just giving you the details. And this is just one microsection I took out of this particular study. And again, a better quality microsection. Obviously, I was having a good day. But you can see the microsection. You can see the thickness of the intermetallic. We were looking just to see the impact of that on higher temperature. Again, no real issues whatsoever. So I just wanted to include that. And I also wanted to mention about preforms. Now, preforms have traditionally been used for intrusive reflow or connector reflow in general. But when we talk about solder bricks, as I refer to them generally, we're talking about blocks of solder, extra solder, which may or may not have flux on. But all it's doing is adding solder to the joint. So if you're a contract manufacturer or a company that can't change their hole to lead ratio, I appreciate contractors may not be allowed to change because they're customers, but I just really do not ever understand why, because the customer should understand that really it's never going to affect the quality or reliability of the board in any way or electrical characteristics, in my opinion. But if you can change the hole to lead ratio, you don't need solder bricks or greater volume of paste. But if you are in a situation where you can't change anything and you have large holes which you can't fill with solder paste, then solder bricks work well. So all you're doing is adding more volume of solder, and the flux which is in the solder paste is sufficient to allow it and the solder brick to reflow. So these two examples are before and after placing bricks on the surface. And bricks, these particular images are actually from India. However, a number of manufacturers of solder bricks are available within the industry, not just Indian, but they are one company. And you can see a close-up of the brick in place. And this is one of my video clips just showing a brick from another supplier being used, and you can get a feel for how this actually works. The solder paste is reflowing on the surface of the board normally. When it's in a liquid state, the brick also reflows and pulls the solder into the plated through hole. So again, it's giving you that extra volume during the reflow soldering operation. And the nice thing today is you can get SAC alloys and low temperature solder bricks. So again, they're available for all of the different processes that we're using today. So when we talk about reflow soldering considerations, then, this is general, but also there are advantages for our process that we're talking about. The key thing, obviously, is you pick a reflow process for the volume you're going to be doing, the speed you want to run your process, ideally. So you could use a relatively small oven, and I've used 4-zone ovens to do intrusive reflow. Again, it comes down to how many you want to do. So if you want to be doing 1,000 boards a day, then you're going to be looking at a bigger, longer machine typically. But if you're running a low temperature process, because you can get faster reflow at lower temperatures, then you might be back to an 8-zone as opposed to a 10-zone oven. The key thing with any reflow process, you want to get the minimum delta T, difference in temperature, in the oven from side to side, from top to bottom, etc., and between zones, and obviously on the board you're actually assembling. So that's why we do profiling. Another thing to consider is exit temperature. And exit temperature and cooling are important sometimes for the surface finish, and quite critical when you're talking about OSP and tin finish, because the quicker you reflow and cool the board down, the less it affects the solderability of the board for second side reflow. And it's something that quite often is misunderstood. Nitrogen can help, but high temperature up, high temperature down still has an effect on the intermetallic structure, but also has an effect on wettability and solderability. So nitrogen is useful in certain situations, but it's not necessary on other situations. Also, key things are looking at how you do profiling for your particular machine, whether it's reflow convection or vapor phase, but what changes in the process. And I normally like to use wetting measurements to see the impact of changing any process conditions. And again, that's something slightly out of context from what we're talking about today, but it's a useful thing to be able to do. Another thing to do is look at the surface of the board you're going to be processing. And I'm not talking about solderability, I'm talking about the actual solder mask. Because with intrusive reflow, you may be printing solder paste directly onto the surface of the solder mask to get the volume required. But if you've got poor solderability or poor wettability, then it's not going to be drawn into the plated through hole. And what you want to happen is the solder to be drawn into the plated through hole and leave virtually no residues on the surface of the resist. So on the example on the left-hand side, you can see nothing went in the hole. On the right-hand side, everything went in the hole, but there's still evidence of residue in terms of solder particles on the surface. Now, you'll always see flux there, and of course, the more paste you use, the more flux you will see. That's obvious, but there's still some particles on the solder resist. So you pick your solder resist to minimize the possibility of residues being left. Now, for those of you who are not familiar with vapor phase, this is just a batch vapor phase system. And the boards are loaded to a carrier. They're lowered into the vapor, the condensing vapor, held for a period of time. And I've speeded up this video. They're soldered and then they come out. It's a very simple process. You can get inline as well as batch systems, but again, all of these systems can handle what I'm talking about today, which is intrusive reflow as a process. So just to show you a couple of examples, first of all, of profiles. In this example, we've got a maximum temperature of reflow of 233 degrees Celsius with a temperature differential of 3 degrees C. Now, you will always get, contrary to popular belief, a variation in temperature even with vapor phase as opposed to convection, but it will be smaller, generally speaking, than convection reflow. And that's the art of profiling to get the best result, the best process for your particular product. So if we look at convection reflow, you're all familiar with this. Basically, we have a system with multiple zones. We run a board through the process. If we've got more than so many zones, we can adapt the profile and change it nicely to minimize the delta T. In this simple example, the hot bits I've indicated with red spots, and the blue marks are the cooler parts of the board. And there could be somewhere between 3 to 10 degree differential between these areas on the board. And you, me, and every other engineer works to reduce that delta T. But if you're going to be running pin-in-hole intrusive reflow, the connector quite often then becomes the demanding part of the process. So we must monitor the connector. And you would normally monitor the connector with a thermocouple underneath the connector. This is underneath the body of the connector because that's where the paste is being reflowed initially, not on the opposite side. And typically you'll find the center of that connector, because of the mass of the connector body, will be the coldest part on that particular board. It's better to have more than one position you're monitoring when you're doing profiling, but certainly pick the coldest bit if you're not going to pick multiple positions on the board. So in this example, exactly the same board, you can see the difference. We've got a maximum temperature of 242 degrees Celsius, but we've got a differential of 15, and this is on a convection reflow. We could do better, I'm sure, and it depends obviously on the capability of the machine, but I'm just trying to show you that there is an advantage with vapor phase on minimum delta T's, but we should be able to do better than this example I show you from a project I was working on. So back to the connector, and just to get a feel for the connector and reliability, this is a couple of years back, but we took a series of boards that we produced with Intrusive Reflow, 100% fillets, and they were temperature cycled at MPL. They went through 1,000 cycles, then they went through, as it shows you here, 2,200. Typically it would just be 2,000, but possibly somebody left it in a little bit longer. And it's minus 55 to 125, which is a typical military style temperature cycling with no failures. But I would have bet a car that we would never have a failure on joints that we'd already demonstrated was sound to start off with. But it's just nice to have some data. So if you just look at the visual appearance, it's worth pointing out that it's fairly easy to solder through hole and intrusive reflow joints, but when you're looking at large holes, as we've got in this hold down feature that I've shown you before, you will never fill that hole. I've worked in factories where people see this process working beautifully, and then they see a hole in a joint and want it filled up. Well, why? It's a hold down feature. If you test this connector, the pin will either break or the pin will come out of the connector body before that solder joint ever fails. So really it's irrelevant. But we do want solder around where the pin is. So that's why we have that crosshair design, but not crosshair between 12 o'clock and 6 o'clock and 3 o'clock and 9 o'clock, where we're indexed round by 45 degrees to get a solder joint on the hold down feature. That's why it's there, just literally to be able to do that. Now back to just having an example of X-ray, and I've included this video clip which I did with a Dage system about 2 years ago, I think it was. And what we're looking at here is intrusive reflow, again of the paste, and you can see the paste has pushed out. You've got the lollipops on the end of the pins, but you can see how beautifully it pulls back. And it's all to do with the length of the pin protruding and not pushing it too far out. But again, it shows it, and it allows us to look at any outgassing or voiding in the plated through holes at the same time as you're running the profile, which is kind of nice. So you can see I'm indicating the top pins and the bottom pins, or the top side of the board and the bottom side of the board in this particular case, so we can see what's actually happening in the process. So when you reflow solder paste in holes and on pins, it does tend to fall off occasionally. Because if you've got too much push out onto the pins, or the pins are too long, when it goes through reflow, prior to it going out or exiting the preheat zone, some of the paste may be dislodged. And I just show you here, this is a machine I was running at Productronica on a production stand, and you can see some little balls sitting on the heater banks. And on the right hand side, I've got a piece of copper that I ran through the process directly underneath boards, and you can see the little spots. And it was just a way of demonstrating, you know, what is actually happening in the process. So what you're trying to do is minimize that, and by correctly specifying materials and also the lead lengths, then you eliminate this particular thing happening. This is a random phenomena. So yes, not on connector pins, more on hold down features, you're liable to see this because there's a greater volume of paste in those particular areas. So back to my example, talking about making sure the solder mask is right. On the last two examples, I showed you that ideally the solderability or the solder resist wasn't right, but on this example, all of these pastes have reflowed successfully on this green solder mask, and there's no separation of particles. The point I'm trying to make here is evaluate the solder mask you're using on your boards to eliminate this possibility. and then make sure purchasing always inform you that they're potentially changing boards and possibly solder mask finishes, and find out in advance whether they're compatible or not. It's simple to do. Print paste onto the resist, run it through the pizza oven, and see if you get any separation of particles. It's not in any specification for solder mask. Solder mask was not designed to have paste reflowed on it. We do it, and if you pick the right combination, you shouldn't really have a problem. Another thing to bear in mind that hopefully you'll never come up against, but outgassing from boards. If you're familiar with boards in wave solder and selective, we can get pinholes and blowholes. Well, that's due to outgassing from the plated through hole. So if you're putting paste in a hole and a pin and reflowing it, the same thing could occur. So in these couple of examples, this is just me testing a board to demonstrate that it's the board that's gassing, causing the problem, nothing to do with the soldering process. So again, it's just something to stick in your mind. If you start to have problems with voiding, it's not necessarily paste and profile. It might be something else within that combination of products that you're running. So I mentioned about sort of the testing, and this is just another little study where we've got 2 lead-free alloys. You can see here we had all these surface finishes and temperature cycling again, similar to what we talked about before, minus 55, 125, with a dwell at 40 minutes, so 40-minute dwell at each part, each extension, the highest and lowest temperatures. I'll think of the word to discuss that later on. But so dwells at the maximum and minimum that you would see. This is the board, and up the end, the top, the bottom there, you can see the connectors. And again, in terms of soldering performance, perfectly okay, 100% fill, and really we didn't see any issue whatsoever. And there is actually an MPL report on this particular study, but it was right in the very early days of lead-free technology when people were looking at different finishes, etc. So really don't really see any issue at all in terms of through-hole reliability. So what I've tried to do in this webinar this afternoon is talk about intrusive reflow, the basic premise on how it would work in terms of hole to lead ratio, etc. How we get the paste onto the printed circuit board by printing, which is the predominant technique and the easiest technique to initially implement. Jetting technology, we can assist solder joint formation using solder preforms, or we could use solder preforms by themselves if you wished. So those are the techniques. We've briefly talked about the reflow process, which is convection or vapor phase. Both work perfectly well. And I've highlighted some simple reliability studies that we've done on intrusive reflow and been extremely successful with those processes. So what I'd like to do is see what questions you would like to ask. So if you have any questions at all about pin and paste reflow, any aspect that I've talked about so far, then just type them directly into the control panel and I'll do my best to answer those questions for you. There's a couple of questions already come in. If you have some questions, just type them in. Just a reminder that every month I do a webinar on a particular subject. I've already listed, and you'll see when you receive a copy of the slides directly after this session, the topics that I've got coming up over the rest of this year. But we do have a webinar on demand service. So if somebody has a particular subject they'd like to hear about, I did a webinar for a company in the US on die and pry or die and pull testing of BGA packages last week. So again, if you have a particular subject you need your team trained up on, then again, that's something we can do for you. Or alternatively, there are lots and lots of that webinars that are recorded And again, you can have access to many of those topics. Okay, so let's pick up on some questions. So first one, there's, just bear with me a second. Let's have a look. So somebody asking a question about outgassing. So basically with outgassing, it's moisture in the printed circuit board. If you have moisture in a board and it can find its way out either in breaks in the plating, thin plating, porosity in the plating, then the water will turn to water vapor and literally just bubble out as you saw. So what you were seeing in that simulation, or me testing a board, is oil. I'm heating up the board and I'm seeing the water vapor come out. So the oil is allowing you to see the gas. But the same thing would happen if that was molten solder. You just see it go plop, 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 plop. You wouldn't see the actual gas emanating, but you'd see the effect of it. So using the oil is just such a useful, great technique to test boards. Next question. Okay, oh yeah. So how do you do the gassing test? The gassing test, I can send you, if you're interested, just drop me an email after the webinar, a procedure. But fundamentally, you take a board, you get some high temperature oil, you put 1 or 2 drops into the hole, you make sure there's no bubbles in the hole to start off with, just to avoid confusion. Then you take a number 7 bit, soldering iron bit, 700 degrees Fahrenheit. You place that on the track going to that plated through hole or on the plated through hole pad, and you make contact. You shine a light underneath to allow you to illuminate it, see it nice and clearly, and within 1 to 3 seconds you'll see gassing. If you don't get any gassing at all, then clearly the plating is sound, there's no moisture in the board, which would be uncommon, but seriously the plating and the coverage is sound, so that shouldn't really be an issue to you. But if you're interested, drop me a separate email and I'll send you a copy of the procedure on how to do that. Right. Pietro asks, vapor phase in combination with vacuum can solve board outgassing. It's an interesting question. Personally, I don't believe it will. Yes, it will get voids while the solder is in a liquid state. But just before going from liquidus to solidus, you wouldn't be able to pull a vacuum and get rid of that gassing phenomena. The other thing is that you've got to be so careful when you're using vapor phase and vacuum. I mean, I've screwed up. I've done it wrong. I've done it properly, but you've got to make sure you don't pull a vacuum too fast with any vacuum soldering process. Otherwise, yes, you suck out the voids, but you also suck out all the solder with it as well and make a real mess inside the machine. So it is not difficult to get the right specification of a board and eliminate the problem of gassing in the first place. So again, it's a board issue and should be dealt with your board manufacturer. Next question, for modified stencil apertures, right, okay. In terms of clearances, the minimum would be whatever the stencil manufacturer is comfortable with. So what we're trying to do is get a volume of paste which is going to fill the hole. Now you can do a calculation to calculate what volume you need to fill the hole, so that's fine. But when we're talking about the little bits of metal between the square apertures, again, it's down to the minimum the material you're using from the stencil manufacturer will allow. So on those examples, they are 10 thou. I've gone down to as low as 8 thou tangs, but again, you've got to be careful that you don't damage the printed circuit board. You don't damage the stencil during use. So again, the first instance is finding what the stencil recommendation is before you start specifying what you want. So find out what they can do. That's the first thing I would do. For convection reflow, what is the maximum temperature change you would want between zones, and maximum temperature between PCB temp and zone temp? Well, the first thing you do with any reflow process is you've got to decide on what you're going to be reflowing and the throughput you want. Otherwise, you're trying to run 1,000 boards through a four-zone oven, or you're running 50 boards a day through a 10-zone oven, which doesn't make any sense from a commercial and an energy point of view. So that's the first thing you want to do. In terms of reflow profile, the next thing you want to do is look at what the recommendation of the paste manufacturer is. Now, originally, if you go back, I don't know, 20 years ago, every profile from every solder paste manufacturer was exactly the same. There was nothing really different about them. Nowadays, because of the importance that suppliers put into the performance of their paste, their rheology, the reflow characteristics, the fluxing, the deactivating of fluxes for low residue, no clean, they will give you recommendations for each of the processes. So that's your first starting point. Then the next thing is to try and minimize the delta T. So if you're starting off with a 10-zone oven, let's say, and you're trying to go at 50 centimeters a minute, then again, you should be able to have a lot of flexibility. If you need to change the delta T on particular high mass boards, connectors, BGAs, etc., think about what else you can change in a reflow process. A lot of people have a 6-zone, 8-zone oven, and the top and bottom heaters are set the same. But why? So the first two zones may be, let's say, 120, 120. Next one may be 140. You could actually have the one below it 150, 160. Remember that although in reflow we are talking about zones are all convection today, generally, you still got a metal heater which is blowing hot air through a metal lump, if you like. It's got a capacity there. So there's radiation there. So if you change your settings and you do your profiles right, you'll be able to know your oven a lot better. So consequently, you'll be able to make those changes. But having the zones top and bottom always, reproducing themselves is not necessarily what you really need. Every manual for every reflow oven will tell you that. But if you think about it, a bit of common sense, if I've got a little bit of more heat I need to put into a board, I don't want to put all the heat from the top side. I want to balance it. So potentially I can do that with most reflow ovens. So that's the thing to think about. So that's the sort of sequence that I would normally go through when setting up a process. Next question is, do you ever have any solder balls with intrusive reflow? The only two times I really have solder balls is one, when they're spat out from the joint, which would be gassing, which is generally unusual today, and incompatibility of solder resist or solder mask. There are a few occasions on designs that I'm asked to review where the connector hasn't been considered. Remember I mentioned that if you have a paste design, the connector has to sit over that paste design and not make contact with the paste. Otherwise, it stops the paste reflowing apart from underneath the connector, and you get little solder balls or little solder beads. Another reason why you can get, with intrusive reflow, little solder balls somewhere around the connector is where somebody has manually inserted it, but they're new to the job and they can't get in the hole first time, so they disturb the paste. So that's another reason why you might see it, but that'd be fairly unusual. In terms of subtle failures, there's a gentleman here talking about, connector temperature. Probably the most subtle failure that you can sometimes get, particularly on IDCs, installation displacement connectors, again, where a connector is close to its limit. And what you can see sometimes is the connector pin in the housing moving. So rather than being held in place with all the others at the same height, sometimes you can see the connector pin slip down a little bit. So its actual length is longer on the bottom side. But that's either too high a temperature, or the connector pin is not being retained properly in the housing. So again, that's another reason why you might see it. So just a reminder, if you've got any more questions, just type them directly into the control panel and I'll do my best to answer them. Just while we're waiting for a few more questions to come in terms of intrusive reflow, as I said, I've been doing it for many, many years. It's a standard process in manufacture today. I think it's fairly easy to adopt. It's certainly easy to try out just with a scrap board. You could make a connector. You could make a stencil with some cardboard and cut some holes. You could do something very, very basic and simple just to get a feel for the process. So really have a go. There's nothing really to stop you with having a go. Profiling, do you find there is a difference between connector pins? Okay, yeah. Yes. If you've got a connector which is, let's say, 2 inches long, for argument's sake, or 2 inches long, or 50 millimeters for new measurements, and the body of the connector, the bulk of the connector is on one side, so you've got pins coming out, let's say 3 rows, you will tend to find that the connector pins close to the body of the part will be a lower temperature. So if you do a temperature profile, so connector pins on 3-4 rows will be lower close to the body and higher the further away you go from the body. And high and low temperatures on the rest of the pins on a 50 millimeter connector, as I said earlier, right at the ends of the connectors will be the hottest bit, and right in the middle of the connector group of pins will be the coldest bit. And that will be true of pretty much any connector you come up against during profiling. The other thing is I tend to always mount the thermocouples underneath the connectors, and I generally, if I'm going to use the board multiple times, I would actually snip off the pin and mount the thermocouple in the hole that pin would be in. So you're actually in the board directly underneath or adjacent to the connector. It's just guarantees that the thermocouple is not going to move and you can use it multiple times. Otherwise, normally I'd always use high temperature solder, or I would use aluminium tape for any other positions on the printed circuit board. Okay, next question. Do you have any problems with excess flux? It's a good question. You must realize that with more paste volume will come more flux. It's intuitive. So if you already know that you've got X amount of flux, and that's either an issue or not issue, then you need to address that at the start. So if you're doing in-circuit testing where you're probing connectors, then the amount of flux left behind will be slightly more than on the rest of the board because you're using more paste volume. If it's not an issue with you having slightly more paste volume, more flux volume on the pins, then fine. If it's a case that electrical test will be affected at some point, then you need to have a word with your solder paste manufacturer and look at a lower flux content or more flux which is burnt off during the reflow cycle. So again, if you're putting more paste down, you're going to get more flux. That's a given. So you just got to engineer your way around that. So any more questions? Just type them directly into the control panel and I'll do my best to answer them. There is no more at this moment in time. But if you've got any more questions, just type them directly in the control panel, and I'll do my best to answer them for you. Just a reminder that at the end of the webinar, there is a couple of survey questions just on the webinar, its content, my performance, and hopefully my performance hasn't been affected by my recent eye surgery, but hopefully not. You will be receiving a copy of the slides shortly after the end of the webinar. And of course, as I said, you can visit the website, 007 website, for a copy of my book, which is free, on intrusive reflow.